Hi, everybody, and welcome to another exciting edition of Mr. Duncan Teaches Us Math. Today, we're going to be talking about piecewise linear functions. For those of you saying to yourself right now, what in the world did he just say? That's a piecewise linear function. You've never heard of it before, likely as not, but you are going to learn about it today. Some of you will be experts by the time we're done. Others of you will be very knowledgeable about what you're doing. All right, so here's the problem that's prompting what we're doing. Let's say for the sake of argument that you're trying to hire a clown for your birthday party next week. You talk to Bozo, who tells you that for 3 hours or less, he charges a flat fee of $100 plus $50 per hour. For more than 3 hours, he charges $250. Stop. I am going to check to see if you are paying attention to what you're doing, and I'm going to change this to 175. I made a little boo-boo, but this will be a good check to see who did the homework and who just copied or made stuff to look pretty. He charges $175 plus $25 per hour. Graph his total charge compared to the number of hours he works, and develop the equation to find the total cost given any number of hours. All right, so what are we being asked to do? First, look at your question. Graph his total charge versus the number of hours. So there's our y-axis. There's our x-axis, number of hours, total charge. This is nothing new. And then develop the equation to find the total cost. So we're going to graph something. We're going to find the equation for what we just graphed. The first part will be pretty easy. The second part, not quite so easy. Okay, first one. For 3 hours or less, he's going to charge $100 plus $50 per hour. So let's just talk about it. For 1 hour, he charges what? $100 plus 50. Oh, not what I meant to do. $100 plus $50. So I'm going to put it at 1 hour, comma, 150. For the next one, he charges $100 plus 50 for 2 hours, so $200. For the next one, $100 plus 150, so for a total of $350. Okay. For 4 hours, we can no longer use that first equation because remember, he just told us we're talking about that rule for only 3 hours or less. When we get to 4 hours, we need to use this second rule that he came up with, 250, which is really 175, because of the correction I made in the first slide, 175 plus $25 per hour. All right, so for 4 hours, we've got 175 plus, actually, let's start with 3 hours. Even though we can only do more than 3 hours, let's start with 3 and see what happens. 175 plus 3 times 25. That's 175 plus 75, which is 250. Okay, and so the first point there, even though we can't really use it, would be 3 comma 250, and that's the reason it's actually right on top of that last red one that I had drawn, and that's the reason that I changed this to be 175 because I wanted the points to overlap at the point where x equals 3. For the rest of them, we don't have to worry. So when we go to do the next one for 4 hours, we've got 175 plus 4 times 25, which is 175 plus 100, or 275. Okay, so my next point is going to be at 4 comma 225, which is going to be right about there. Okay, great. The next point after that, 175 plus 5 times 25, which is going to be 300. We're getting the pattern here. The next one will be, that's for 5. For 6, we'd have 325, etc. Okay, this is all linear, so the patterns are easy to see. So 5 comma 300 and 6 comma 325. I'm just going to move that just a hair. If it would let me move it just a hair. Okay, great. And really what ends up happening is we get this relationship here. I've already got these because I knew what I was going to be doing. Okay, and what I'm going to do now, I am going to try to get rid of these points just to make it easier to see what happened here. Look at that. We have the first part gives us that's from 3 hours or less, and we've got a pretty steep slope. It's $50 per hour is our slope, $50 over 1 hour. So we go up 50 every time we go over one. The second part does not grow so steeply, as you can see, and we go up $25 every time we go over 1 hour. So obviously the slope is going to be less steep. But this whole equation, this whole graph here, even though it has two distinct parts to it, part one and part two, even though we have that, it is still the description of what's happening here, and we need to come up with an equation that describes this whole graph, not just part of it. That's what we're doing today. That's called a piecewise function. A piecewise function, you can pause this as soon as I reveal it to copy it down, and then you can start again. A piecewise function is a function that is defined differently for different intervals on the domain. Or in easy language, it's a function that looks different depending on the input or x value. Okay? What that means, if you look back here, we can see that you have something that clearly looks different. The red clearly looks different than the green. Okay? They're just, the slope is radically different. That's a piecewise function. It's when your function is defined differently for different intervals on the domain. Look at this regular function down here. I'm going to cover that up so you can't see it and pretend you didn't see it. Regular function, f of x equals 2x minus 3. That is a function that looks something like this. I'm going to sketch it real quick. Do not bother to copy it down. It has a slope of 2, and its y-intercept is negative 3. It's going to look something like that, say. Okay? And pretend that was a straight line. It looks consistent for the whole interval. For a piecewise function, the two that I have down here, f of x equals, now I have two different functions that f of x equals. So this is strange already. F of x either equals 3x plus 2, or it equals 4x minus 3. Let's look at the rest of it. It equals 3x plus 2 when x is greater than 5. It equals 4x minus 3 when x is less than or equal to 5. Okay? What I want you to do as we start graphing this, I want you to first note that I have changed my interval to be counting by threes, just so these fit a little better on the graph. We are not going to be using anything in quadrants 2 through 4. We're only using quadrant 1 here. And we're going to talk about this function, this piecewise function right here. What I want to do, I want to graph this linear equation right here, 3x, or actually wrong color. I'm going to do it in orange. I'm going to graph 3x plus 2 on the domain x is greater than 5. Let's just graph 3x plus 2 to start with. We know that this is a function that has a slope of 3 and a y-intercept of 2. My y-intercept 2 is right about there. And my slope of 3 means I go up 1 over 1, up 1 over 1, up 1 over 1. Okay, so up 1 over 1, or sorry, up 3 over 1. My next point would be right about there. My next point right about there. My next point right about there. Right about there. Right about there. Because I'm counting by threes on my y-axis here. So when I'm going up 3, I'm really just going up one space. And then I go over one space because I'm still only counting by ones on the x-axis. Okay? This is, of course, x and y. Now what I'm going to do, I'm going to replace these ugly dots I have with a line. I'm going to make sure it's the right color. That doesn't look anything like a line. I'm going to replace this with a line, I say. And it's going to look just about like that. Okay, now only one problem. Look at what this says. It says for x is greater than 5. Look at what I've done. I've graphed a whole bunch of stuff where x is not greater than 5. Look at all those x values that are not greater than 5. And I have graphed for it. Okay? So what I'm going to do, I'm going to draw myself an imaginary line at x equals 5, okay? And I'm going to say this function I've just graphed only works on that side. So what I'm going to do, I'm going to erase all of this down here because that's the wrong value. That's the wrong equation to use when x is less than 5. What I'm going to do, in effect, is I'm going to shorten my line so that it starts at x equals 5, or x is greater than 5, really. So what I really should have, because this is only for x is greater than 5 and not for x equals 5, at the very end here, I should have an open circle. Okay? Actually, I can just do that here. I will just have an open circle. Okay? So this is the graph of 3x plus 2 when x is greater than 5. I am missing only one thing. That thing is an arrow right there because it does go on forever. Now what I want to do, I want to graph the other part of this. Notice I want to graph what happens when 4x with 4x minus 3. This is for all the x values where x is less than or equal to 5. I'm going to do the same thing, though. I'm going to graph this function as if it were a regular function, and then just take away the parts that can't be. 4x minus 3 means I have a slope of 4, and my y-intercept is minus 3. Okay, so I am in the wrong color here. I have a slope of 4. So when I go, this is really, if I kept the scale the same, this is really negative 3, negative 6. So my y-intercept would be right here, and I'm going to go up 4 over 1. I'm going to wind up right about there. And then I'm going to go up 4 over 1. I'm going to wind up right about there. By the time I'm going to go up 4 over 1. By the time I get to where x equals 5, I have 4 times 5 minus 3, which is 20 minus 3, or 17. So 5 comma 17, what do you know? It's right there in that point where the other one left off, almost like I did that on purpose. I did. Okay, so now what I'm going to do, I'm going to do the same thing. I'm going to draw a line that matches that, which would be right there. But notice what I know. I know that this is only for the values of x that are less than or equal to 5. That's these right here. Okay, so I cannot go above this imaginary line. This imaginary line right here, I can't go to the right of it, so I'm going to take my graph and I'm going to reduce it down. Okay, and so what I have done now, once I erase some of this, I have this function that is actually going to meet at this point, so I don't need this hole anymore. I have this function here that goes on forever in one direction, growing at, which looks like the function 4x minus 3. I have this other one in the other direction that looks like the function 3x plus 2. Okay, and they are going to be on the same graph. Now what I can do, I can go back to the original problem that we were working on, and I can describe this function. I didn't know how to before, now I should know how to, or at least have a stronger idea of how to do this. To describe this function, I'm going to say f of x is equal to, and it's going to be two functions. Okay, this first one here in red is the function 50x, so $50 per hour, plus my y-intercept, which is 100. 100 plus $50 per hour. The second one, notice they give me everything I need right here. My slope is $25 per hour. My y-intercept is what I start with, 175. So it's going to be 25x plus 175. Although, what did I do wrong here? In order to be a piecewise function, I need to describe when it should be each of those things. When should I use 5x plus 100? Or sorry, 50x plus 100. When should I use 25x plus 175? This is 50x plus 100 for x is less than or equal to 3 hours. 25x plus 175 is when it's more than 3 hours, so 4x is greater than 3 hours. Okay, so this is my piecewise function. This is two parts. When x is less than or equal to 3, I'm going to use this function here. When I have more than 3 hours, I'm instead going to use this function here. And that's the way I'm going to graph piecewise functions. Check my time right here. Okay. Okay, let's go on. Another example, I'm going to actually skip this one for time purposes. Congratulations. So if you're watching the video, you can just do this fun thing. Skipped. And we'll move on to the next question. I want to point out that you can also have a non-continuous example. What continuous means is when you look back on this previous graph right here, the points meet, or the two parts of our line meet at a single point. Same thing previously. The 2 points meet at a single point, or the 2 parts of the graph meet at a single point. This does not always have to happen, as will be the case here. Let's graph these two functions. H of x equals 3 minus 2x. All of us who are now experts at graphing equations know that our slope is -2 and our y-intercept is 3. So let's go ahead and graph this first part. This is going to go through the y-intercept 3 and have a slope of -2. So down 2 over 1, down 2 over 1, down 2 over 1. And I'm using my magic pen, so let's quickly go through those points before they all disappear. Okay, we've got something like that. The next, but before I can go on, I know that this is only valid for when x is less than or equal to 1. So I draw an imaginary line at x equals 1. Okay, sorry about that. I know that I'm going to draw an imaginary line at x equals 1. And I know I can only count the part that is less than or equal to that. So I need to truncate, or that means make shorter this line here so that it only works from 1 and below for my x value. And because this equal sign is here, I know I'm going to end this with a filled in circle. And mine's not real pretty. It's hard to be precise on my computer, but on yours you can make it pretty. The next one I'm going to draw, this guy right over here, -2x plus 9. I know my y-intercept is 9. And so I am going to change to my pen. My y-intercept is 9. And I know that my slope is going to be, again, -2. So I'm going to go down 2 over 1, down 2 over 1, down 2 over 1, etc. And I'm going to end up graphing something that looks a little bit like this. I think I've messed up these because they should look roughly parallel because they have the same slope. So I think I've just messed this one up a little bit. I'm going to change it just so they look, again, on yours, it's a little bit easier to do because I'm working with my finger here. All right, so I've got these two functions. Notice they do not intersect at all. This second one, though, I never did fix this and make sure that I have the second line with my domain x is greater than 1. So what I need to do is I need to draw that imaginary line at x equals 1. And I need to make sure that I'm only counting the stuff on the right of it. So I need to change this line just a little bit so that it looks about like that. Okay? And this is a non-continuous example. All we did in summary is we graphed this and we only count the part when x is greater than or is less than or equal to 1. Then we graph this function here and we only count the part when x is greater than 1. All right, I'm going to have you guys work on this example here. 1/2 x minus 7 when x is less than or equal to 4, and 5x minus 25 when x is greater than 4. Okay, it may be continuous, it may not be continuous. You do have to graph this though. Easiest way to do that is to think about your slope and your y-intercept. Your slope and your y-intercept, and keep in mind when you are graphing which piece of it. Okay? One more final example. I'll try to do this as quickly as possible, just to show you that you don't always need to have two pieces. You can do this in 3 or 4 or 5 or 7 or 1,000 different pieces for your function. You just need to have a different interval set up for each one. Here we have 3 intervals. When x is less than -4, when x is between -4 and -2, and when x is greater than or equal to -2. I've made this very easy to make it quick to graph. When x is less than -4, my value for y is just -6. So look what I can do. I know that my value -6 is right here. So I'm going to draw this line at about -6. Okay. But, oh, again, with the magic pen. -6. Not even close. That's close. Okay. -6 is right there. But again, keep in mind, you have to be only there for x being less than -4. So I draw an imaginary line at x equals -4, and I know everything to the left of it can count, so I need to get rid of everything to the right of it. So watch me truncate this line so that I go to -4. Great. I'm going to skip to the next part here, or the third part here, because that's really easy as well, and then we'll just do one slightly hard part. The value of y is 2, so I draw a line where y is 2, and that's right there. And this is when x is greater than or equal to -2. So I'm going to draw an imaginary line at x is -2, and I know I can keep everything to the right of it, so I have to get rid of everything to the left, because this line is only valid when x is greater than or equal to -2. So I truncate this line for the line. Okay, come on. Okay, we'll just do it that way. Okay, having trouble. Okay, great. So that's where x is greater than or equal to -2. So one other thing that we forgot to do here, for this one, -6 for x is less than -4. This is x is less than, it cannot equal, so I should finish this one with an open circle. This one here, x is greater than or equal to -2, so it can actually be equal. I'm going to finish this one with a solid circle. And then this last part, all I have to do is graph y equals 4x. 4x goes through my origin because there's no y-intercept, so the y-intercept must be 0, and it goes up 4 every time I go over 1. So I've got 0, 0 as 1 point, up 4 over 1, up 4 over 1, down 4, left 1. And so that is my line there. I'm going to see if I can match it. And then I'll try to get a little closer on that. That looks like about right. Now I'm going to erase these points that I had drawn. And I need to think about the interval here. The interval only works for x is in between -4 and -2. So -4 and -2 is the only part of this that works. So what I need to do is I need to draw, or I need to truncate this so it's only working for that little bit. Okay, so at -4, I'm going to put a closed circle because I know it can, or I'm sorry, I'm going to put an open circle because it cannot equal -4. So I put an open circle. I made a mistake there. I put an open circle where x is -4. I put another open circle because it can't equal -2 either, an open circle there. And then I get rid of everything else. And my function will look something like this. It is very strange. If I'm going to follow this function from left to right, I go left up until here. I have to drop down when I get to -4, and then I follow that up. And then when I get to -2, I have to jump all the way up and go along that way. So this is another piecewise function just to show you that it can actually be 3 pieces. Thanks for bearing with me, folks, and I will see you in class.